What if the atom, the very bedrock of our reality, isn't some tiny solar system with little particles zipping around? But what if it's actually more like a musical instrument? And all its weird quantum properties, they're just the notes it's allowed to play. Well, a pretty incredible new paper is proposing exactly that, and it might just change how we look at everything. Let's get into it.
So to really appreciate why this idea is so out there, we first have to understand the puzzle it's trying to solve. You see, for more than 100 years, physics has kind of had this split personality. We've got the classical world, the one we live in and see every day, and then there's the bizarre, super strict world of the very, very small, the quantum world.
I mean, just think about the difference here. In our world, a planet can orbit the sun pretty much anywhere it wants, with any amount of energy. Everything is smooth, continuous. But an electron around a nucleus? Oh no, it's totally different. It gets forced into these very specific, locked-in energy levels, and it can only exist in these particular orbital shapes. It's like the universe has a strict set of blueprints for every single atom, and there's no deviating.
And that right there brings us to the mystery that has kept physicists up at night for decades. Why are the rules so rigid? Why is the atom quantized? The standard answer from quantum mechanics is basically because. That's just how things are. The rules are the rules. But what if they're not?
A new paper by Harold White and his team suggests a pretty mind-bending alternative. They're saying the answer isn't buried in some abstract quantum rulebook that we just have to accept. Nope. It's been hiding in plain sight this whole time, in the very fabric of what we call empty space.
Their entire theory hangs on this one really powerful question. What if the vacuum of space isn't actually a void? What if it's a physical medium? Something real that can be shaped, something that can vibrate, and that can carry waves right through its own structure.
They've got a name for this. They call it the dynamic vacuum. So instead of thinking about an empty stage, imagine space is more like an invisible ocean, or maybe a huge block of jello. It's a physical thing that can be disturbed. And if an atom exists inside this medium, well, then its environment isn't empty at all, and that changes absolutely everything.
Okay, so how do we get from this idea of a vibrating vacuum to a real working atom that actually matches what we see in the world? Well, the model says you only need two key ingredients. First, the proton at the heart of the atom isn't just sitting there. It's actively imprinting a structure onto the vacuum around it. It's changing the vacuum's properties in a very specific way. And second, this vacuum medium itself has a built-in physical rule, and it's called dispersion. Now, this rule is the key that connects the shape of a wave to its frequency, or, its energy.
Dispersion is the absolute linchpin of this whole idea. It's a well-known concept. A prism splits light because of dispersion, right? The glass material makes different colors, different frequencies of light bend just a little differently, and they split apart. So in this model, the vacuum itself is dispersive. It has its own built-in rule that connects how big a wave is in space to how fast it oscillates in time.
And this is where it gets crazy. When you combine that proton's imprint on the vacuum with this physical rule of dispersion, something incredible happens. The equations you get to describe the vibrations, they become mathematically identical to the Schrödinger equation for the hydrogen atom. I mean, without any of the usual quantum assumptions, the math just falls right into place.
So what does that mean? It means all those weird quantum rules we've just learned to accept for a century, they might just be the natural music of the cosmos. As the authors say themselves, quantization, the whole idea of these separate, discrete energy levels, it isn't some strange, fundamental rule we have to build everything on top of. In this model, it just arises naturally from the physical properties of their dynamic vacuum, just like the specific notes of a violin are a natural result of the properties of its strings and its body.
And the results are, well, they're stunning. These aren't just abstract equations on a page. The standing sound waves that the model predicts for the vacuum around a proton, they have the exact same shapes as the electron orbitals we actually observe in a hydrogen atom. The s, p, d, and f orbitals, they all just emerge as the natural harmonics, the resonant frequencies of this vibrating medium.
The visual match is one thing, but the numbers are where this theory just becomes mind-blowing. Look at this table. The model's predicted energy levels for these notes aren't just close to what we measure for hydrogen, they're identical, down to 9 decimal places. Just think about that kind of precision. All it takes is one single calibration, and the entire energy structure of hydrogen just clicks perfectly into place.
And it gets even deeper. In standard quantum mechanics, all those other quantum numbers, the ones for angular momentum, they're also just part of the rules you have to accept. But in this model, you don't need them as assumptions. They just emerge naturally from solving the wave equation on a sphere. They're simply a consequence of the geometry of the situation, kind of like the overtones that naturally appear on a ringing bell.
Okay, so let's just step back for a second. What does all of this really mean? If this model holds up, it's not just a new way to look at an atom, it's a pretty profound shift in how we might view reality itself. So here's the ultimate takeaway. All those weird quantum rules are not fundamental rules at all. They are emergent properties. The atom isn't a collection of particles following bizarre instructions. It's a resonance. It's a stable pattern of vibration, a song being played on the instrument that is the vacuum itself. All the weirdness, it's just the acoustics of the universe.
I mean, this reframes the whole foundation of quantum physics. It suggests that underneath all the strange, counterintuitive rules, there might be a more classical, more physically intuitive reality just waiting for us. And it leaves us with this one last provocative thought. If the simple hydrogen atom is a song, a complex vibration in the fabric of space, what other, more complex music is the universe playing that we just haven't learned how to hear yet?